Swayam Prabha. Digital India. Educated India.
So let's try to see how we can define a addition and multiplication in GF to the power of 8. So in order to understand, like GF to the power of 8 addition, the first thing to see is whether what is x plus x. Okay, so x is an element of GF to the power of 8. Okay, and I want to add it with itself. So as I mentioned that if I take two elements, say ax and bx, so these are two elements from this field GF to the power of 8. You can conceptualize this by taking it 2 bytes. Okay, so both of them are bytes. So GF to the power of 8 is a byte of data, and bx is also another, like ax is a byte, and likewise bx is another byte. So this is, like how you can conceptualize ax and bx. Both of them are elements of GF to the power of 8. So you can also have, you can conceptualize them as bytes, you can conceptualize them as polynomials. These are different ways of abstracting what ax and bx stand for. And now I want to define, say, the operation ax plus bx in GF to the power of 8. So the way to do that is by doing a modulo, like bit by bit modulo 2 addition. So modulo 2 addition bit by bit. So if you do it bit by bit, then it turns out that this is nothing but an XOR operation. Okay, so what I mean is, suppose let's take an like an example. Suppose 1 0 1 0, okay, and maybe 0 1 1 and 1. So this is one example of an element of GF to the power of 8. Okay, as I told you, you can also have a polynomial representation of this. Likewise, you can take another example of GF to the power of 8, right? So maybe you can tell me 0 1 1 1. Like I'm just giving an example, 0 1 and maybe 1 and 0. So this is another example of GF to the power of 8. So how do I do an addition? I will do a bit by bit addition. So I will do a 1 plus 1 XOR 0, so this will be 1. 1 XOR with 1, this is a 0. 1 XOR with 1, this is a 0, and so on. Okay. So I'm just doing bit by bit XOR operation. Okay, so like this, you have got 0 and 1 is 1, 1 and 1 is 0, 1 and 0 is 1, and 1 and 0 is 1. So this is nothing but which is Cx, which is the summation of Ax and Bx, right? So if this is how you define the addition, then you can tell me what is x plus x. So that means that I take Ax and I add it with itself, right? So in the truth table that I showed about XOR, if I XOR 1 with 1, what do I get? 0. 0 and 0 is also 0. So therefore this will be 0 actually. Okay, so if I add x with x, it is 2x in normal algebra, but the 2 is in this case 0 because we are doing modulo 2 arithmetic. In modulo 2 arithmetic, 2 stands for 0. Okay, so this is very important to understand. So these are actually also called as, given the fancy name of characteristic 2 and so on. So, you can ignore this at this point. Okay, so now let us try to see what is the implication of this. So that means that if I take, like say an element of GF to the power of 8. So let me take an example of GF to the power of 8, which is 0 0 0 0 0 0 1 1. What is the polynomial representation of this? It is 1 plus x or x plus 1, right? And suppose I want to do x plus 1 square, then what? So x plus 1 square would be x plus 1 multiplied with x plus 1, right? So this essentially stands for x squared plus 2x plus 1, but as I said 2 is 0 because 2x is 0, so this is nothing but x squared plus 1. Okay, so this is a funny mathematics. You see that x plus 1 whole square stands out to be x squared plus 1. Right? So therefore, right, we can do addition in this manner, and here we have seen how to do a squaring. Okay. So now we will see, like that this is fine. And you can similarly, like, it is quite convenient also in terms of implementations, because in this case, in this particular mathematics, your coefficients of the polynomials are either 0 or 1, right? So you really do not have large coefficients. In normal arithmetic, normal algebra, you deal with very large coefficients, right? Because when you multiply, it can increase. When you add, it can increase. But since you are doing this modulo 2, your coefficients are always either 0 or 1, right? So they are very easy to implement in hardware, in on microprocessors and so on. So now what we have seen how an addition works. I think we will try to understand how a multiplication works, and that is a bit more complicated. So suppose I have got two elements, say I call this as ax and call it as bx, and I want to multiply them. Okay. So in this case, I have got x power of 7 plus x power of 5 plus x power of 3 plus x. This is one element. I want to multiply it with x power of 6 plus x power of 4 plus x square plus 1. So if I multiply them, then it is easy for you to see that, you will get terms like x power of 7 plus 6, because 7 and 6 will get multiplied. So you will have x power of 7 plus 6. And likewise, these are your corresponding terms. Right? So now if you arrange them in a suitable manner, you will see that you will get, if we arrange them, you will get this x power of 13 plus and so on. Okay, out here you note that 2x power of 11 will go to 0 because of the reason why I said just now. Okay, but the point that I want to kind of emphasize here is that you will have terms like x power of 13, right? And now the question is this does it belong to the field of GF 2 power of 8? So in GF 2 power of 8, if I take an element, then the highest degree can be x power of 7, isn't it? Because you have only 8 bits to represent. So if you have got terms like x power of 13, it naturally doesn't fit in the field, right? So you have to do something, right? And that something, yes? Yeah, it's very simple. What you just do is you take a polynomial, you divide with that polynomial, and you take the remainder. So you need to define a special polynomial, okay? You need to define a special polynomial so that if I want to take ax and bx and I want to define ax product of bx, then it will be the normal multiplication that I do with ax and bx, okay, in modulo 2, except that I will do a modulo of this mx. Okay, so this is my special polynomial. Okay, so in AES you will find out that there is in the specification of AES there is a suggested polynomial. Okay, so these polynomials are also called as irreducible polynomials, and I will not go into what it means in this class, but it is good to know that they are called as irreducible polynomials, something like prime numbers that we have in the normal numbers. Okay. So in this case, we need such a polynomial so that I can take that polynomial and I can divide that polynomial and take the remainder. The remainder should be belonging to GF 2 power of 8. So what does it tell you about this polynomial? One thing that you should be able to tell immediately from the polynomial. Can you tell me that? What should be the degree of that special polynomial? X to the power of 7 or x to the power, okay, suppose it is x power of 7, then what would be the maximum degree of the remainder? 6. But your remainder can go to 7. So what should be the degree in that case? X to the power of 8. Because if you take the polynomial with x power of 8 degree and you divide it, the remainder will have x power of 7, right? No, I am saying that suppose you have got this polynomial, I want to do a modulo with mx, right? Such that the remainder is having x power of 7 as degree, right? So then what should be the degree of this mx? Should be 8. Because if it is 8, then only I will get this in 7. No? Okay, x power of 13 will go to 5. Okay. But if it is, say, if I take any polynomial, say I call it as, say, Cx, okay, and if I divide it by modulo x power of 8 plus something, then this remainders coefficient can go maximum till x power of 7.
Yes, sir.
Right? Do all of you get this point? Right? So that is why you will see that this particular irreducible polynomial, it is not probably very difficult to understand. This is the suggested polynomial. It is x power of 8 plus x power of 4 plus x power of 3 plus x plus 1. Okay? This plus and XOR are similar actually in this case. Okay? So now here is an example. Suppose I take a bx polynomial and if I multiply it with x, okay? So your bx is b7 x power of 7 plus whatever, right, till b0, and if I take and multiply with x, then I can get an x power of 8 term, but now since I am doing a modulo with this, I will be able to make it smaller. Right? I will be able to make it back to the finite field. Right? This is the only Galois field that you need to know at this point. Okay. So now so here is an example, just to show you that if you do it right, then you will get the degree in x power of 7, but it is probably not very difficult to understand why the remainders degree will be maximum x power of 7. So now once we have understood this, you are good enough to understand the various operations. Okay. So let me discuss two important operations. One is the S box. So the S box of AES, or the byte sub as I mentioned, is nothing but a lookup, right? That is, it takes a byte and replaces it by a byte. But internally it does, you can actually, so if, of course, you can, you need to build this table, right? And you can imagine that the table you can imagine the table to be made out of, like an 8-bit input and an 8-bit output. Okay? So what would be the size of that table? What I can do is, imagine that the S box has inputs which go from A0 to A7, and the output is, say, B0 to B7, because the input is an element of GF2 power of 8, the output is also an element of GF2 power of 8. So I can conceptualize that to be an 8-bit to 8-bit lookup, right? So now what I do is I store this in the form of a table where I have got some rows and some columns. Okay, so I use, say, the first 4 bits to get the row and the next 4 bits to get the column. That means I use A0 to, say, A3 to index a row and A4 to A7 to index a column, right? Okay, and every element here stands for a byte because it tells me what is B7 to B0, right? This is what is the size of your S box lookup, right? So the S box lookup will have therefore size of 16 rows multiplied with 16 columns multiplied with 8 bits, right? So that is basically 256 bytes, right? So you can represent this in the form of a lookup, right? But that's not always a very good implementation, particularly when you are talking about a hardware implementation, because you need to store in the memory and the memory will be slow and so on. So in AES, there is a very nice mathematical representation of the lookup as well. So that representation is made by 2 sub operations. Okay. So one, which is, so the operations are made of 2 sub operations. The first one is an finite field inverse. Okay. And the second is an affine mapping. So let me explain quickly what does it means. So what is a finite field inverse? I have already defined to you what is a multiplication, right? So it means that I know how to take two polynomials ax and bx where they are elements of gf to the power of 8, and I know that ax into bx is nothing but the normal multiplication of ax with bx modulo with mx, right? This we know. So now the finite field inverse means that if I give you an element ax, the finite field inverse of ax will be such that if I take ax and if I multiply with its inverse, okay, with this like definition of multiplication, then I should get back 1. So 1 stands for 0, 0, 0, 0, 0, 1, right? This is essentially this representation, this binary representation stands for 1, right? So we know that every element, okay, except 0, like the all 0, should have a finite field inverse. So therefore I can define this in this manner here as told over here. That means that if A is 0, then the output is 0. If A is not 0, then the output is nothing but A inverse. Okay, I can define this in this manner. And then it is followed by an affine mapping. So affine mapping means I take the result of this A inverse and I store this in the form of this vector of dimension 8 and multiply with a constant 8 cross 8 matrix of size 8 cross 8 but filled up with elements belonging to zeros and ones. This is a part of the specification. Okay, so it's a constant matrix. Now I add another vector. This vector is called as B. So what I do is therefore after this first affine mapping, so this finite field inverse, if my input was A, I transform this into say A dash, okay, which is the result of computing this finite field inverse, and then I take A dash and I multiply A dash with this fixed matrix, call it as A, and this vector call it as B, and I multiply this in this manner. So I get A, this is your A, and I add plus B. Okay, so this A multiplied with A dash plus B, and that gives you my output C. So you can of course do a lookup in this manner. Equivalently, you can also do this operation. They should be same. The table is built in this manner. Okay. So now I want to tell one, I will not have time to go into this, but I will just tell this because I think somebody asked me this. That is the way this S box is constructed is very carefully constructed. Okay. There is completely, we can devote few hours, or maybe few lectures on this, how the S box is constructed and why it is constructed in this manner. So one of the important requirement of this S box is that it gives you the much needed nonlinearity to the cipher. Okay. And it gives you the confusion property to the cipher. So why? I think there was a question, right? That why does it give confusion? So you see, the way the cipher is constructed, you see, if I take the plain text, okay, the first thing that you do is an XOR with the key. And then you pass it through these S box layers, right? So you have got these various 16 S boxes. So let's consider one such byte of the plain text, maybe P0. You are XORing the 0th bit of the key and you are passing it through this S box. Okay? So note that if this transformation is not linear, is not nonlinear, then this idea of round will not work. So what you can do is you can collapse all the rounds to a single round, and then you can actually do an attack very simply. Okay, and I can discuss offline on this, but I don't want to probably elaborate or get into this in this class. But what I want to rather say is that this is a very important requirement from the classical security point of view of the cipher, that the S box has to provide sufficient nonlinearity to the cipher. Okay, and what it should do is it should make the construction in a manner so that from the output of this it is difficult to tell what is the corresponding key. So it basically will hide the property or the relationship between the ciphertext and the key because of this convoluted property of the S box. Okay, so if you look at this S box, like this, so at the end of the day, this is the lookup, right? So you see that the S box means that there are, like 256. If you think in the form of a Boolean truth table, you have got 256 inputs, right? and the corresponding outputs you can denote as like B0, B1, B and so on till B7. So what I mean is each of these S boxes here like B0 is a Boolean function of A0 to A7, right? So B0 is a Boolean function of A0 to A7. Likewise, like B7 is also a Boolean function of A0 to A7. Okay? So if you observe the Boolean functions, you will see that they are extremely complicated. Okay? If you want to write down them in a piece of paper, you will see it will take you several pages to write down these equations. Okay? And the reason why they are complicated is because they want to provide the much needed classical security to the cipher. Okay? But there is one problem with this kind of constructions. Although they are good, but they are very complex. Okay? And that is why if I increase the dimensions, like maybe make a 16 cross 16 lookup, then it will be so large that I cannot get a very easy implementation. So that is why the S box has to be small, reasonably small, 8 bits. But you still want a byte to byte diffusion. And that is why you need to complement this S box by a suitable diffusion layer. Okay? And that brings us to the next part of the construction, which is the shift rows and the mixed columns. Okay? So now let's see how this works. So I'll get into this. And so this is my first part, which is the round key, which you have already seen is a very simple layer. That is followed by the shift rows and the mixed columns. So I will quickly talk about the shift rows and the mixed columns. So first, let us try to see what is the shift row operation. So in the shift row operation, you take this 4 cross 4 state matrix. The first row, you don't do anything. So you see here it was AEIM, it remains AEIM. Okay? In the next row, you basically make a cyclic shift to the left by one step. That means, B comes here, F goes there, and likewise there is a shift. So you can see here it becomes BFJN becomes FJNB. Right? There is a cyclic shift to the left by one byte location. For the second one, you also do a cyclic shift, but now you do it by two steps. Okay? And for the third one, you again do a cyclic shift, but that is with 3 steps. That is equivalent to doing one opposite shift. Right? So is this clear? Why? It will soon make sense. But is the idea clear? And then you have, so this is your shift row. So if you have got shift row, the inward shift row is also very simple, right? You can define in a similar manner. And now let's see the mixed column operation. This is the most very important step. Okay, so what you do here, as the name suggests, you do, so the previous one was a row-wise operation. This one is a column-wise operation. Okay, so what you do here is you take, say, one of these columns and you transform them into another column. How do you do this transformation? Is you take this and you pre-multiply that by this matrix. So this is a mixed column matrix. Okay. So this has got these numbers 2, 3, 1, 1 and then cyclic shift of 2, 3, 1, 1. Okay. So the first row is 2, 3, 1, 1. Second row is 2, 3, 1, 1 but cyclically shifted. Again you have got 2, 3, 1, 1 cyclically shifted. 2, 3, 1, 1 cyclically shifted. It may be emphasized here that these 2, 3, 1, these are not normal integer numbers. These are also elements of GF 2 power of 8. Galois field 2 power of 8. Okay, yeah. Okay, very good question. So they are part of the specifications, which means it is always this matrix. Okay. So one of the reasons why like this is nice, because first of all like this matrix has an inverse, that is very important. Okay, for the decryption. Second thing is that if you want to like multiply something with 2, say this is an element of GF 2 power of 8 and maybe there is another element of GF 2 power of 8, then doing this operation is very simple. How will you do this operation? You just do a left shift. But if there is an overflow, then what will you do? So what I mean is, suppose you have got an element, say Ax is 1 1 0 0 0 1 1 1. Suppose these are Ax, okay? And I want to do 2 into Ax. So then what will it be? It will become, of course it will be 1 because I will do a shift like this. It will be 0, it will be 0, this is 0, this is 1, this is 1, this is 1 and this is 0. But then there is this extra 1 also sitting over here. So what do I do with this? How can I bring it back to the field? So think in the form of a polynomial, okay? So what is this coefficient? This is 1, this is x squared, x cube, x power of 4, x power of 5, x power of 6, x power of 7, and this is x power of 8.
So we can multiply by x and then take
So your result is what? X power of 8 plus x power of 3 plus x power of 2 plus x, but this is not in the field. So just now we discussed, right, that how do you bring it back to the field? Right. So you basically do a modulo with that mx, right? If you do a modulo with mx, then this result will be back to the field. Okay? And I leave it to you as an exercise to think that you can do it very easily. So what is mx? Mx is x power of 8 plus x power of 4 plus x power of 3 plus x plus 1, right? So what you can do is, you can write x power of 8 as x power of 4 plus x power of 3 plus x plus 1 and can just substitute it over here. So this will become equal to x power of 4 plus x power of 3 plus x plus 1 plus x power of 3 plus x squared plus x. Okay? And this is nothing but x power of 4 plus 2x cube, but that is 0. Okay? Likewise, x plus x is 2x, which is 0, and you will have x power of 4 plus x squared plus 1. So this is back to GF2 power of 8. Okay? I am just doing modulo mx. You can verify that this is the same as modulo mx. Addition and subtraction is same in Galois field. Yes. Yeah. Yeah, I leave it to you as an exercise to think. That is exactly how you can do the, like division and then the remainder. Okay, so the question that is asked, just repeating the question for the sake of everyone, is that why did I write this x power of 8 equal to x power of 4 plus x cube plus x plus 1? Okay. So my answer is not really an answer, but rather a question. Okay, so that you should verify that if I take this polynomial, do a modulo with this mx, I get the same result when I just replace this by this x power of 8 with this term x power of 4 plus x power of 3 plus x plus 1. Yes.
the polynomial should be x to the power 8 plus x to the power 7 plus you made 1.
Yeah, maybe. Maybe I have missed. That is possible. Let me just go back and check. Yeah, no, I think this is the polynomial, right? X power of 8 plus x power of 4 plus x power of 3 plus x plus 1. This is your irreducible polynomial, the special polynomial.
No, that is fine. I'm saying about the 2 into x.
Okay.
Yeah, that 2ax. That is 1 1 0 0 0 1 1 1.
Oh, okay. I mixed this x power of 7. Okay, yeah, okay. Yeah, that is, thank you for pointing it out. So this will be, yeah, so then there will be an x power of 7 here basically, right? Okay. So you can do this 2x in this manner. And now, how can you do 3 into x? 3 into x is x plus 1 multiplied with x, right? And that is nothing but 2 into x plus x. Because x into ax is nothing but 2 into x. Okay, so what I mean is that the coefficients are chosen very carefully so that the implementation becomes easy. Okay, if you want to do 2 into certain polynomial, then the result from 3 into that polynomial is easy to obtain, because you can just use 2 into that polynomial and add it with itself, you will get 3 into that polynomial. So you do not need to recompute this basically. Okay. So anyway, so the thing is that this is the prefixed matrix. That's the point. Okay. So therefore now what I will do is I will take this polynomial matrix 2 3 1 1, 2 3 1 1 and 2 3 1 1 and 2 3 1 1, and I will just pre-multiply with this column to get this resultant column, and this I will do for all the columns, all the 4 columns. This is what is the definition of mixed columns. So is the definition of mixed columns understood? Yes? No?
Sir, I want to ask, sir, then while we are multiplying by 2, when we have to multiply by x.
Mm-hmm.
So like when we multiply by x, why is it the same as multiplying by 2?
Okay, well, so this what I wanted to say is that this 2 that I see over here is a Galois field 2. So this 2 is nothing but the polynomial x, right? And likewise this 3 is nothing but x plus 1. So I think the question was, when I multiply 2 with some element, why do I multiply with x, right? So 2 is a representation in binary format for x, right? So you see that the way we were representing these elements is, if I take, you know, like 0 0 0 0 and 0 0 1 0, this stands for 2, right? So if you look at this from the polynomial point of view, this is nothing but x. I know it is slightly confusing because I think we are speeding up things, but I hope you gather it. Okay? So likewise 3 will be what? 0 0 0 0 0 0 1 1, and this stands for x plus 1, right? So like this you can do all the other computations. Right? This is understood to all of you?
Sir, we calculated ax by doing x in 2x by x into x.
Right.
We can also do it by ax and XOR with ax also.
X XOR with x? I didn't understand the question. Can you repeat the question?
We have to calculate 2ax, so we
Yeah.
put x into ax.
Right. 2 into x is nothing but x multiplied with ax.
Yes, sir. And sir, 2 into ax is also ax XOR with ax.
No, that is different. So don't confuse things actually. So when I said x, okay, so question was, okay, these are quite pertinent questions actually. Okay, so it is not unusual that the question comes up. So you are saying that x plus ax, I am saying 2x, and that we saw to be 0. Okay, so this is a wrong thing at this point, because x plus x is just 0, because you are taking 2 elements, you are adding it with itself, that is 0.
Yes, sir.
Okay, but when I am talking about 2, where 2 is an element of GF 2 power of 8, that is different. Okay, so here this 2x just means x plus x. Okay, so I think it is better to avoid this 2x at this point. So it just means that if I summarize what I had meant so far, is that the addition is defined by taking a polynomial ax and taking another polynomial bx, and you do a modulo 2 bit by bit addition. That is how you define addition. If you want to define a multiplication, you take ax bx, multiply the polynomials, do a modulo with this special polynomial mx. That's it. Okay. So now so in this case, particularly for this particular matrix, the elements are GF 2 power of 8 elements. So 2 means x, 3 means x plus 1, and 1 means 1. Right? Any questions? If you have any questions, you can please feel free to ask. Modulo 2 addition bit by bit is exactly the same as doing XOR. Okay?
So this coefficient 2, 3, 1, 1, where we were shifting it to the left or right?
Okay, so this is nothing but, when you are doing x into something, right, that's a cyclic left shift. It's a left shift. So what I mean is the question was, why is 2 into x. So 2 into ax means basically x into x. So what is x into x? So all the degrees of ax are getting added with 1, right? So that's a shift to the left. Huh? Dimension of matrix is this matrix only. It is fixed matrix. Sorry? Why will you scale up? No. So, okay, good. So, there are very interesting questions. Let me answer this question first actually. So, the question was, if I want to multiply x with ax, you have got, so imagine that ax is what? Something, like just think about something like maybe x power of 4 plus x power of 3 plus 1. This is an example of ax, okay? When you are multiplying with x, then it becomes x power of 5 plus x power of 2 plus x, and that is nothing but a a left shift of the representation of ax.
Yes, sir. But sir, when it overflows.
When it overflows, then you have to do this modulo mx. Then of course it is not shift. Right? Then of course you have to do this extra operation. So it is a shift plus a conditional XORing with this irreducible polynomial.
Yes, sir. Like if it was 1 1 0 0 1.
Yes. This is precisely the example that I gave here.
Yes, sir.
Then you have to do an extra modulo mx operation.
So sir, there instead of cycling shifting, it becomes something else.
No, then it is not cyclic shift. Okay, so x into x is a cyclic shift when there is no overflow. But when there is an overflow, then you have to do a shift. I mean, first of all, it is never a cyclic shift, it is a shift, left shift. Okay, it is a left shift, and if there is an overflow, it is a left shift plus this modulo mx operation. If there is an overflow. Yeah. What was your question? So the dimension of this matrix is, like a 4 cross 4 matrix, and every element is a GF2 to the power of 8 element. So if you want to multiply, like this E, F, G, H basically, then what you do is, let's work out the first element here. This will be what? 2 into E plus 3 into F plus G plus H. Okay? So this is your first element. So this corresponds to this E. Right? Likewise, there will be 3 more elements. So now if you observe this particular term, you are having an element in GF2 power of 8 which is E, and there is another element in GF2 power of 8 which is 2. You are doing this multiplication just the way we define now, and likewise for 3F, G and H, and all of them are GF2 to the power of 8 element, and you know how to add the GF2 to the power of 8 elements. Right? So you get another GF2 to the power of 8 element. So if you get another GF2 to the power of 8 element, your E is a GF2 to the power of 8 element, your F is also a GF2 to the power of 8 element, G and H are all GF2 to the power of 8 elements. Right? Do you understand the mathematics of mixed columns? So the question was, what is the original dimension of the state of AES, right? No, I did not understand the question. Can you be a bit more clear? Which matrix? This matrix is prefixed to have a 4 cross 4. Because of the way the AES state matrix, see the first thing that, the question was, why is this matrix a 4 cross 4 matrix, right? So it is a 4 cross 4 matrix, first of all, because you are doing a column by column operation. Okay? And in the column of the AES state, how many bytes do you have?
16.
You have got 4 bytes. Right? You have got 16, but I mean there are 60 elements, but in one column there are 4 bytes. Right? So this 4 bytes you need to replace into another 4 byte element. So you need a 4 cross 4 matrix for doing that. Right? And also it has to be reversible, which means from the output column you should get back the original. Right? So you need to have an inverse mixed column as well. Does it make sense? Good. So now let us try to see why or how do they work together. Okay. So for this I will maybe take a little bit of Yeah, maybe this space is good enough to explain to me this. So what I mean is, see the, like the combination of the shift rows and mixed column. This I think is the most, the most elegant aspect or most beautiful aspect of the AES algorithm. So please pay attention, okay? So if you focus on this part and learn this part, this is good enough. The rest you can forget, okay? So this is so nice. So the idea here is that if you take a shift row, okay, and imagine that there is a disturbance of 1 byte in the state matrix of it. 1 bit gets affected, okay? So if 1 bit gets affected, maybe this bit lies in this byte, okay? So what does it happen therefore? Because of the shift rows operation, nothing really changes because the first row remains in its own position, right? So it remains, the disturbance remains over there, but there is an S box, so therefore, right, this is but still localized to 1 byte. So this is what happens after the shift rows operation. Now there is this mixed columns which comes in. Now the mixed columns is designed in a specific manner for which if there is a disturbance in one of the input bytes, then all the 4 output bytes gets corrupted. Okay? So now, what is the implication of this? If you follow this by the next shift row operation, another shift rows, then what will happen? This will remain here. This will probably, go here. This will come here and this will come here. Right? Because remember in the shift rows, the first row does not shift. The second row there is a cyclic shift by 1 and second and 3. Okay? So now if we apply a mixed columns on this by the same property, what will happen is everything will get disturbed. Okay? All the columns will get disturbed because of this thing will propagate to this column, this will propagate to this column, this will propagate to this column, and this will propagate to this column. Right? Because the mixed columns will operate column by column. Na? So in this column, right, there is 1 byte which is disturbed. So therefore in the output this entire thing is disturbed. Right? So therefore, right, there was a 1 bit change here, and that 1 bit has created, a phenomena where the entire thing can get, pretty chaotic. Right? So in only 1.5 rounds, actually 2 rounds, you basically get a phenomena which we called, or which we like to call as an avalanche. You know what's an avalanche? In the glaciers you get avalanche. So we see a phenomena like that. That's why you get a diffusion property. So this is why we have this nice combination of confusion and diffusion. A single bit change can propagate to the entire state matrix in such a nice manner. And that is why you have got these 2 things together. But tomorrow we will see how we exactly exploit this and get the key by using something which are called as fault analysis. So I think if you have gathered this till this point, then this is again summary of what we have seen. I think we are now pretty much in a position to get to the, to understand how, side channels work. So we have been, seeing various kinds of side channel sources, but I will be trying to talk about, and I think I digressed from the power consumption point, and I'll get back to that power consumption discussion and see how we can do a power analysis of the AES algorithm.